What is a general chemical equation for a combustion reaction?
A combustion reaction involves the burning of a hydrocarbon in the presence of oxygen to form carbon dioxide and water as products. A specific example would be CH4 plus 2O2 CO2 plus 2H2O in general. The equation for a combustion reaction will look something like hydrocarbon plus oxygen equals carbon dioxide plus water.
What is a free radical?
A free radical is an atom or molecule that contains unpaired electrons in one, or more, of its orbitals. Typically these species will be highly reactive as the unpaired electron, s, can pair with other electrons in a favorable manner. Radical species can have any charge or be neutral.
What are Fraunhofer lines?
When scientists first began observing the spectrum of light reaching Earth from the Sun, the spectrum contained many dark lines, which indicated that light of certain wavelengths wasn't present in the sunlight. These are now called Fraunhofer lines, named after their discoverer. And they are caused by the elements in the outer atmosphere of the Sun absorbing certain wavelengths of light, which prevents those wavelengths from reaching the Earth. Understanding that Fraunhofer lines were caused by atomic absorptions was one of the earliest examples of atomic spectroscopy.
Why are chemical reactions important in biological systems?
Chemical reactions make everything in your body work. This is true in all living things, plants, animals, insects, bacteria, etc. Anytime you make even a slight movement, lots of chemical reactions have to take place. Digesting food, building up or breaking down fat, breathing, cell reproduction, or pretty much any other process that happens in your body involves lots of chemical reactions. Chemistry isn't only important in the lab, it's essential to everything related to life.
What fraction of the oxygen on Earth is produced by the Amazon rainforest?
It is estimated that about 20% of the diatomic oxygen, O2, on Earth at a given time was produced by the Amazon rainforest.
How is analytical chemistry used in medicine?
Analytical chemistry techniques are routinely used in many areas of medicine. When your blood is drawn, for example, the doctors use techniques borrowed from analytical chemistry to determine levels of several analytes in your body, including cholesterol, vitamins, glucose, and white blood cells. Analysis of tissue samples and other biological fluids is also based on analytical techniques. Other examples of medically related applications include tests for illegal drugs and steroids. Glucose sensors used by diabetic patients, or to check for toxic substances in your body if you are exposed to hazardous chemicals.
What is cooperativity?
Cooperativity describes how the binding affinity at one site of a protein affects the binding affinity at another site. In hemoglobin, for example, there are 4 sites at which oxygen molecules can bind. After the first oxygen molecule binds, conformational changes take place in the rest of the protein that increase the binding affinity at the other sites. The second oxygen is then able to bind even more easily, and the third and fourth even more easily yet. This gives rise to a sigmoidal curved shape in a plot of the fraction of hemoglobin bound by O2 versus the partial pressure of O2, see illustration. Similar binding curves result in other examples of cooperativity. Though the example of hemoglobin is probably the most commonly discussed example of the phenomenon.
How is hydrogen produced for use as a fuel?
Most of the current hydrogen production in the U.S. is carried out by steam reforming natural gas, methane, which involves reacting steam with methane to generate H2, to make hydrogen a viable fuel source. More efficient ways of producing hydrogen on the large scale will be needed. Many scientists are currently investigating chemical and biological catalysts capable of carrying out a process called water splitting, which is the production of H2 and O2 from water, H2O. Water splitting may have the potential to make hydrogen into a viable fuel source for vehicles.
What are the 12 principles of green chemistry?
The 12 Principles of Green Chemistry, as originally suggested by Paul Anastas and John Warner, and explained by us, are as follows: prevention. The best way to minimize the environmental effects of chemical waste is to prevent waste from ever being generated in the first place. It's easier, and better for the environment. If we can minimize the amount of waste we need to treat, clean up, or store. Atom economy. The idea behind this principle is that chemists working on developing synthetic methodologies should generally strive to incorporate as many of the reagents as possible into the final product. This helps to prevent the generation of chemical waste and also helps to reduce the quantity of reagents that need to be produced in order to generate the ultimate target. Less hazardous chemical syntheses. Chemists are encouraged to seek out synthetic routes that avoid or minimize the use of highly toxic chemicals. In addition to trying to minimize the total quantity of waste, we also want to minimize the toxicity of the waste we generate. Designing safer chemicals in addition to minimizing the toxicity of the waste generated during a chemical synthesis. Chemists should strive to select synthetic targets that will also be low in toxicity or have minimal negative impact on the environment. Safer solvents and auxiliaries. Whenever possible, chemists should seek out routes that avoid the use of large quantities of solvents, separation agents, or other chemical auxiliaries. When these cannot be avoided, they should be used in minimal quantities. And the choices that are safest for the environment should be made. Design for energy efficiency. The energy costs of synthetic methods should be considered and minimized whenever possible. This may include carrying out reactions and workup procedures at ambient temperatures and pressures. Use of renewable feedstocks. Reagents and solvents should be obtained from renewable sources whenever possible. Reduce derivatives. The number of synthetic steps involving derivatization, such as protection and deprotection steps or use of blocking groups, should be minimized whenever possible. The target of this principle is also to reduce waste and to promote atom economy. Catalysis. Reagents that behave catalytically, and as selectively as possible, should be chosen over reagents that react stoichiometrically. Design for degradation at the end of their functional life. Chemical products should degrade to yield non-toxic products that present minimal threat to the environment. Real-time analysis for pollution prevention. Analytical techniques should support in-process monitoring so that the formation of hazardous substances can be prevented. Inherently safer chemistry for accident prevention. The use of chemicals should be carried out in a manner that minimizes the likelihood of accidents that may be damaging to the environment or to human health. This includes both the choice of chemicals used as well as the method selected for carrying out a chemical process. You may notice that the 12 principles are focused closely on the practical synthesis and use of chemical products, and thus they may need to be adapted somewhat depending on the situation, e.g., basic chemical research, large-scale industrial production, non-synthetic applications of chemistry, etc.
What's in paint?
There are three main ingredients in paint: binder, solvent, and pigment. Binder is the stuff in paint that forms an adhesive so that it sticks to the wall. Unlike glue, it's not a polymer in paint, at least not a fully formed one, but instead monomers or short polymer chains that react, cross-link, to form larger polymer networks as the solvent evaporates. The solvent in paint is there to make the paint solution the right thickness so that you can easily put it on the wall without it dripping all over the floor. Then the solvent evaporates, driving the formation of the cross-linked polymer networks. Pigments are, of course, used in paint so that not everything is painted white. Though white paint still needs pigments to be white.
What are sunspots?
A sunspot is a temporary spot on the sun that appears relatively dark. These spots are caused by magnetic storms that prevent convection from distributing heat evenly over the surface of the sun. This results in relatively cold areas of the sun. These spots may be as large as 50,000 miles in diameter, such that they can be visible from Earth even without a telescope, but that doesn't mean you should look at the sun.
Why is the process of manufacturing ibuprofen an excellent example of green synthesis?
The modern industrial-scale synthesis of ibuprofen has very high atom efficiency, and it has been modified from the original synthesis to be both more environmentally friendly and more cost-effective. The original method involved 6 synthetic steps but used stoichiometric, as opposed to catalytic quantities of reagents, had lower atom efficiency, and produced undesirable quantities of waste. The modern alternative, on the other hand, requires just 3 steps, each of which is catalytic in nature. The first step employs a recyclable catalyst, hydrogen fluoride, HF, and produces almost no waste. The second and third steps each achieve 100% atom efficiency, wow! This process truly represents an ideal benchmark for excellence in green synthesis on the industrial scale.
What are the benefits and challenges of using water as a solvent?
The advantages of using water as a solvent are numerous. Water is plentiful, environmentally benign, spans a wide range of temperatures while in the liquid phase, and cuts down on waste. Of course, if there weren't also some challenges to making it work, we would just be using it for every reaction. A primary challenge of using water is that many compounds are either unstable or insoluble in water. Additionally, many reactions that were developed in organic solvents do not proceed. Similarly, under aqueous conditions for a variety of reasons. So the majority of existing knowledge surrounding organic synthesis, most of which was developed under non-aqueous conditions, often cannot be directly applied to reactivity under aqueous conditions. Water can also be difficult to remove from reactions relative to many organic solvents due to its higher boiling point. Since the advent of green chemistry, the amount of research into aqueous synthesis has skyrocketed, and significant progress is being made every day toward the use of water for a growing number of synthetic applications.
What is an isobaric process?
An isobaric process is a process that is carried out at a constant pressure.
How are the quantities on food nutrition labels determined?
The calorie content of food can be determined using a simple calorimetry experiment. The food just needs to be placed inside a calorimeter and burned to determine its calorie content. These days, however, the calorie content of a food can also be determined by simply using standard values of calories in each gram of protein. 4 calories/gram, fat, 9 calories/gram, and carbohydrates, 4 calories/gram. The trick is just to accurately determine the quantities of protein, fat, and carbohydrates in the food, and that's where analytical chemistry comes in particularly handy. The basic idea is that the fat, protein, or carbohydrates need to be extracted from the food. This can be done by choosing an appropriate solvent in which the fat/protein/carbohydrates are soluble, and then using spectrophotometry or one of a variety of other methods, to determine the content of each species in a solution.
What is normality?
Concentration of a solution defined as the molar concentration divided by an equivalence factor. I.e., H2SO4 can neutralize two equivalents of base with its two H end groups. So a 1m solution of H2SO4 is 2n, the equivalence factor of H2SO4 is 0.5.
What is a salt bridge?
A method used to place the two sides, solutions, of an electrochemical cell in electrical contact.
But what if you were to put a catalyst for gas release into a bottle of Diet Coke, R?
That's exactly what a Mentos, R, does. Dissolved gases need a surface to start forming a bubble, let's just assume that's true, which it is. And the Mentos, R, candy provides a huge amount of surface area because it is a very porous material. So add a Mentos, R, and many more CO2 bubbles can form at the same time, which leads to a sugary eruption.
What happens chemically as stars age?
As stars age, they continually produce helium from hydrogen by fusion. So as time goes by, the amount of helium in a star increases and the amount of hydrogen decreases. In order to keep the fusion reaction going, stars heat up and get brighter as they age. Stars also continually give off a small portion of their mass, which generates solar, or stellar, wind. For our Sun, this is an exceedingly tiny amount of material, so don't worry about it vanishing anytime soon. Finally, stars slowly make elements heavier than helium as they age. This is typically quantified by reporting the ratio of iron to hydrogen in a star. Iron is not the most abundant of the heavier elements present in stars, but it is among the easiest of the heavier elements to detect.
How long does it take a chemical reaction to reach completion?
The length of time it takes a reaction to run to completion can range from a fraction of a second to thousands of years. It all depends on how large the energy barrier is for reactants to convert to products. If it's a simple acid-base reaction, like the addition of an HCl solution to water, the reaction will proceed almost instantly. Other reactions can be slower, such as the rusting of a car door. What you first notice as a small spot of rust could take years to spread over the rest of the door. Other reactions can be even slower yet. For example, the slowest biologically relevant reaction known in humans is estimated to take about 1 trillion years in the absence of an enzyme to catalyze it. That's longer than scientists believe the universe has even existed. Fortunately, enzymes have evolved that allow this reaction to take place in only a few milliseconds.
Where are biomolecules found?
Biomolecules are molecules that are specifically found inside of living things and have some function related to life. This includes molecules found in plants, animals, insects, bacteria, or even viruses, which are often considered not to be alive in a technical sense. Biomolecules span a wide range of sizes, some weighing only about 50 atomic mass units, AMU, while others weigh millions of AMU. See atoms and molecules to review the definition of AMU. They are in our hair, skin, tissues, organs, and just about everywhere else in our bodies too.
What is sublimation?
Phase transition from solid to gas without passing through the liquid phase, e.g., the smoke that dry ice gives off.
What are some common structures/geometries for molecules?
The study of chemistry has benefited greatly from knowledge of properties relating to the geometries and, especially, the symmetries of molecules. To get a sense of what shapes molecules adopt, it's worth taking a look at a few of the geometries that come up often in the study of chemistry. One commonly encountered geometry is that of a tetrahedron. Methane has the molecular formula CH4 and exists in a tetrahedral geometry, with angles of approximately 109 degrees between each pair of CH bonds. Linear geometries are also relatively common. Carbon dioxide has the molecular formula CO2 and exists in a linear geometry with a 180-degree angle between the co-bonds. One last geometry we'll look at here is a planar geometry. The molecule BH3 provides one example of a planar geometry. And in this case the BH bonds are separated by angles of 120 degrees. There are also planar molecules with 4 bonds in a plane. And in those cases the bonds are separated by angles of 90 degrees.
What is the theory of phlogiston?
In 1667, a scientist named Johann Joachim Beecher introduced the theory of phlogiston as an explanation for the various observations scientists had made regarding combustion. These observations include the fact that some objects can burn while others cannot, and that a flame in a sealed container can go out before the combustible material is consumed. Beecher proposed that a weightless, or almost weightless, substance called phlogiston was present in all materials that could burn and that this phlogiston was the substance being given off during combustion. If a candle placed in a closed container went out, Beecher said this was because the phlogiston from the candle was moving into the air and that the air could only absorb a certain concentration of phlogiston before it became saturated and could no longer absorb more phlogiston from the candle. Another tenet of this theory was that the purpose of breathing was to remove phlogiston from the body. Air that had been used for combustion couldn't be used to breathe then because it was already saturated with phlogiston.
What is the zeroth law of thermodynamics?
The zeroth law of thermodynamics states that any two systems, call them A and B, that are each in thermal equilibrium with a third system, call it C, must be in thermal equilibrium with each other. Thermal equilibrium implies that the systems must have the same temperature, and therefore systems A and B must have the same temperature. This might seem totally obvious, but it is what puts our use of thermometers to compare the temperatures of different objects on a sound footing. If object C is our thermometer, we can use it to compare the temperatures of other objects.
How is the rate of a reaction affected by temperature?
The rate of a chemical reaction will generally increase with increasing temperature. This is because a higher temperature translates into a higher average energy per molecule, which makes it easier for molecules to surmount the energetic barrier to the reaction. In terms of how this fits into the rate equation, the rate constant K depends on temperature. And K almost always, but there are exceptions, increases with increasing temperature.
What is heat treating a material?
Heat treating can be used to achieve different purposes for different materials. But it generally involves heating or cooling a material to a relatively extreme temperature with the goal of changing its properties. Most often, this is done to make a material harder or softer. Heating or cooling the material allows the internal/microscopic structure to change in a way that is preserved when the material returns to ambient temperature.
What is irreversible reaction?
A reaction in which the products cannot be converted back into the reactants.
What is blood doping in sports?
Blood doping is the act of artificially increasing the number of red blood cells in a person's blood for the purpose of improving athletic performance. This works based on the fact that red blood cells are responsible for carrying oxygen to muscles. And thus more red blood cells can provide more endurance against muscle fatigue. This was originally done by transfusions of red blood cells, either from another person or by collecting and storing a person's own red blood cells to be used later. In the past couple of decades, a new type of blood doping has come about. This is based on the hormone erythropoietin, which stimulates the body to produce red blood cells. Erythropoietin is produced artificially in mass quantities and is commonly used to treat anemia, but is also sometimes used by athletes for the purposes of blood doping.
What is a CD made of?
All types of optical discs, CDs, DVDs, Blu-ray, R, discs, etc., have basically the same components. The outer layer of clear polycarbonate plastic protects the inner layers that contain the data from damage. A layer of a highly reflective metal, usually aluminum, is used to reflect the laser that is used to read the data. The data itself is stored on another polycarbonate layer that contains teeny tiny little pits. The pits are arranged in spiral tracks, just like a vinyl record. If you've ever seen one of those, and are about 100 nanometers deep and about 500 nanometers wide. The laser can detect the change in height by measuring changes in how the light is reflected.
What is an electrochemical cell?
a device that either produces an electric current from or uses an electric current to drive a redox reaction.
What is a transition metal?
Typically, this refers to any element in the D block, groups 3 through 12, of the periodic table.
What is a gamma radiation?
High-frequency electromagnetic radiation can be dangerous to living things.
What is an alkali metal?
Group 1 of the periodic table, i.e., Li, Na, K, Rb, Cs, Fr.
What is a unimolecular reaction?
A unimolecular reaction involves only a single reactant molecule undergoing a chemical reaction to form products. One possible outcome is that the bonds rearrange within a single molecule to form only one product molecule, while another possibility is that the reactant molecule will fragment, producing multiple product molecules.
How can I make invisible ink?
Chemistry principles encountered in this experiment. Evaporation combustion reactions acid/base reactions materials you'll need, cotton swab or paintbrush heat source. Can be a light bulb, measuring cup paper baking soda water grape juice, optional, the procedure. To prepare the ink, just mix equal volumes of water and baking soda and stir well. Take a cotton swab, paintbrush, toothpick, or something similar, and write a message on a piece of white paper using the water and baking soda mixture you have prepared. Allow the ink time to dry. The water will soak into the paper and eventually evaporate. But the baking soda will not evaporate and it will be left behind. To read your invisible message, there are a couple of options. One is that you can hold the paper to a heat source, such as a light bulb or gentle flame. Don't burn the paper. This should cause the baking soda on the paper to turn brown, revealing your message. The baking soda burns faster than the paper, which is why it turns brown before the paper does. Another option is to spread purple grape juice over the paper. You can use a paintbrush to do this. The message should appear in a different color/shade compared to the rest of the paper. This works because an acid in the grape juice reacts with the sodium bicarbonate that you used to write your message.
What are some examples of experimental error?
Say, for example, we use a stopwatch to record the lap times for a race car driving several laps around a track. Our measurements of the lap times will be affected by the quality of the stopwatch. Our ability to accurately operate the stopwatch during each lap, as well as variations in the ability of the race car driver and car to maneuver around the track.
What is the ozone layer and why is it so important?
Ozone has the chemical formula O3, and it is a gas that is naturally present in the Earth's atmosphere. Most of the ozone in the atmosphere exists as part of a layer that sits a few miles above the ground. This is the ozone layer, and it serves to protect the Earth from a significant fraction of the potentially harmful UV light from the sun. Depletion of the ozone layer means that more harmful UV light reaches the Earth's surface. Ozone is also a greenhouse gas, which means that it also plays an important role in controlling the Earth's climate.
Are there alternate theories to the Big Bang Theory out there?
There sure are. While the Big Bang Theory is probably the most widely known and accepted theory surrounding the origins of the current universe, there are still other theories being explored and proposed. Some of these are much more scientifically feasible than others. Take a look around the web and you can find lots of different ideas out there. One alternative that has received notable attention describes the universe as a continuous cycle of expansion and rebirth. The expansion period, similar to that described in the Big Bang, is followed by a period in which the universe once again becomes a dense mass of condensed matter, and then the expansion begins again.
What is valence bond theory?
Valence bond theory is one of two main theories. The other being molecular orbital theory, that is used to explain bonding in molecules. Valence bond theory explains bonding by describing the interactions of atomic orbitals on individual atoms as they come together to form chemical bonds. The basic idea is that orbitals with the right shapes to overlap strongly with each other will form the strongest chemical bonds. Today, valence bond theory's description of chemical bonding based on atomic orbitals has become less popular in favor of molecular orbital theory.
What makes a bowl microwave safe?
Unfortunately, the only definition is an empirical one. Containers that don't get hot in the microwave are microwave safe. Remember, or go look it up now in the world around us, that microwaves heat food by causing molecules with dipole moments to tumble back and forth. If the container has any such molecules, it'll get hot in the microwave. If any water has leached into your ceramic mug, it'll get hot in the microwave, regardless of whether the container gets hot on its own. The food you are heating up will get hot and transfer that heat to the bowl. So be careful when taking hot things out of the microwave.
How do you use pH paper?
Another way of measuring the pH of a solution is with pH paper. This is a paper strip that contains a chemical indicator that changes color depending on the pH of a solution. And it can be capable of determining a very wide range of pH values. To properly use pH paper, it should not be dipped directly into the solution, but rather a drop of the solution should be placed on the pH paper. It can then be held next to a gradient color scale to obtain a pH value. Since this relies on visible color changes, it isn't the most accurate method of determining pH. But it can be a useful tool in the lab for getting a quick estimate of the pH of a solution.
Are inorganic elements important in biological systems?
Absolutely. Not only do ions like sodium and potassium play a huge role in nervous systems, but many enzymes, nature's catalysts, have metal ions in their active sites. Go find a bottle of vitamins and see just how many metals you need daily.
So if the radiation coming from the sun more or less covers all wavelengths of visible light, why aren't plants black?
Let's start with explaining the question a bit more. You can see from the graph on the preceding page that the sun provides light in almost every wavelength. The vast majority of plants, however, appear green, which means they are absorbing blue and red light and reflecting the green light back into your eyeballs. If plants were taking in all the energy the sun is providing, they would appear black, as no light would be reflected.
What is the second law of thermodynamics?
There are several different statements of the second law of thermodynamics, but they are all centered on the idea of identifying what things can happen spontaneously in nature. One formulation of the second law states that, for a closed system, the entropy of the system can only increase or remain the same. In plain language, this says that nature favors having more accessible configurations or arrangements. It's why, for example, a drop of ink in water tends to spread out to fill its accessible volume but won't spontaneously reform a drop of ink. Another statement of the second law says that heat cannot Spontaneously flow from a colder body to a warmer body. Work would have to be done for this to happen, which would imply the process was not spontaneous.
Why did Dudley R. Hirschbach, United States, UNT Lee, United States, and John C. Polanyi, Canada/Hungary, win the Nobel Prize for Chemistry?
For their contributions concerning the dynamics of chemical elementary processes. Hirschbach was recognized for having developed the method of using crossed molecular beams to carry out detailed studies of chemical dynamics. Lee was initially working with Hirschbach, and independently further developed the method of using crossed molecular beams to study important reactions of relatively large molecules. Polanyi developed the method of using chemiluminescence in the infrared where weak infrared emissions from recently formed molecules is measured to learn how energy is released during chemical reactions. Why did Donald J. Cram, United States, Jean-Marie Lane, France, and Charles J.
Why do we need to sleep?
Even though this sounds like a pretty straightforward question, the truth is that scientists still don't know the whole answer. There are several theories, including the idea that sleep promotes restorative functions, that sleep promotes development and structural changes in the brain, that we sleep because it helps us to conserve energy, or simply that it may have been safer for our evolutionary predecessors to remain inactive at night. While there is evidence to support each of these, and other theories, it remains a very difficult question to answer conclusively.
Why did Alfred Werner, Switzerland, win the Nobel Prize for Chemistry?
For his work on the linkage of atoms in molecules, especially in inorganic chemistry. Werner was the first to propose the correct structure of inorganic compounds like Co, NH3, 4Cl2+. He proposed that the cobalt ion was in the center, surrounded by the ammonia and chloride ligands, in an octahedral arrangement. This proposal was consistent with the fact that two isomers of this compound were observed. As the two chloride ligands can be arranged either 180 degrees, trans, or 90 degrees, cis, apart from each other.
What is a quark?
Quarks are the fundamental particles that make up protons and neutrons, as well as several other types of particles. There are 6 types of quarks, which are referred to as different flavors. These are named up, down, top, bottom, charm, and strange. Protons and neutrons are each made up of 3 quarks. 2 up and 1 down quark make up a proton. 2 down and 1 up quark make up a neutron.
What compound was the first to be analyzed by proton NMR?
The first recorded example where the shifts of the different nuclei in a molecule were separated by chemical shift was ethanol, CH3CH2O.
What is substituent?
An atom or group of atoms occupying a designated position in a molecule.
Are all isotopes stable?
Not all isotopes of a given element are stable. For example, tin has 22 different known isotopes, 10 of which are stable and 12 of which are unstable. Though there is some debate about just how stable those 10 are. Stable is, of course, a relative term. Usually when one says an isotope of an element is stable, it means that it has a decay half-life that is too long to be measured by current methods. There are some elements, such as technetium, radon, and plutonium that do not have any stable known isotopes. In fact, no elements with an atomic number of over 83, i.e., more than 83 protons, have any known isotopes that are considered to be stable.
Does reaction stoichiometry also apply to electron transfers?
Yes, for just the same reasons it applies to chemical reactions. The conservation of matter tells us that we must have the same amount of stuff before and after a reaction has taken place, so the number of electrons on each side of a chemical reaction equation need to be balanced for the equation to be accurate.
Why did Hans Fischer, Germany, win the Nobel Prize for Chemistry?
For his researches into the constitution of hemin and chlorophyll, and especially for his synthesis of hemin. Fischer was interested in biologically relevant pigments, specifically those in human bodily fluids like blood and bile, and the green color of plants. He was the first to determine the correct structure for heme B and heme S, which are iron porphyrin molecules, a large ring with 4 nitrogen ligands coordinated to an iron center. These red-colored molecules help transport O2, and other important functions. He also determined the structure of chlorophyll A, which has a structure similar to that of a heme. But instead of an iron, a magnesium ion sits in the middle of the large porphyrin ring.
What is a Lewis structure?
A writing convention in which valence electrons are represented as dots and chemical bonds are represented by lines between atoms.
What is a hydrogen bond?
Interaction between a hydrogen atom bonded to a highly electronegative atom and a Lewis basic atom.
What causes smog?
Smog is caused by chemical reactions involving volatile organic chemicals and nitrogen oxides that take place in the presence of sunlight. These pollutants can come from a variety of sources. But in urban areas, a large quantity usually comes from motor vehicles. These are the reasons that smog often becomes a bigger problem when there is heavy traffic and lots of sunlight.
How is refined sugar different from raw sugar?
Refined sugar is raw sugar that has been purified by a series of steps that ends with crystallization of a sugar syrup into white sugar crystals. The debate of whether refined sugar is worse for you than raw sugar is ongoing. But chemically refined sugar is just more pure sugar than raw sugar.
What are diastereomers?
This is going to sound like a cop-out, but diastereomers are stereoisomers that are not enantiomers. That's the real, technical definition. One type of diastereomers show up when carbon forms a double bond. Recall from previous chapters that when there are three groups bonded to a carbon atom, it will be planar, sp2 hybridized. If the double bond is in the middle of a carbon chain, there are two possible isomers. These two molecules are not superimposable. But they're also not mirror images, so they are called diastereomers. There are many other forms of diastereoisomers, but this form is the easiest to understand.
What are neurons?
Neurons are cells responsible for transmitting information between different locations in the body. Their functions are diverse and include telling muscles to move, passing information from your sensory organs to your brain, making you experience pleasure, and processing information in your brain.
What is a full René?
A fullerene is any molecule made up of only carbon atoms that has a shape of a sphere. Ellipsoid, a distorted sphere, or a tube. The name fullerene comes from Richard Buckminster Fuller, an architect who designed the geodesic dome. Spaceship Earth at Epcot Center is a geodesic dome. The U.S. Post Office recently commemorated Fuller and his geodesic dome on a stamp. Are just a few nanometers wide, but can be up to several millimeters long. The properties of this form of matter are almost unique in the world. And as a result, carbon nanotubes have caught the attention of many chemists. Nanotubes conduct heat and electricity very well, but are also extremely strong, specifically in tests of tensile strength.
What is cracking?
Fluid catalytic cracking is the name for the process that converts high-boiling hydrocarbons found in crude oil into lighter hydrocarbons that are more useful as gasoline and other products. These units operate continuously for years at a time, and there are hundreds of them around the world. In addition to the high temperature and heat that these reactors use to break down long hydrocarbons, there are catalysts used to help speed up the process. These catalysts are usually strong acids in the form of zeolites. Specifically fugazit, which is a mixture of silica and alumina.
What is an amplitude?
The height, or maximum displacement, of a wave.
What is the antibonding orbital?
Orbitals in which the component atomic orbitals are out of phase, leading to repulsion or destabilization.
What is a vapor pressure?
Partial pressure in the gas phase of a substance in equilibrium with its solid or liquid phase.
Why did Heinrich Otto Wieland, Germany, win the Nobel Prize for Chemistry?
For his investigations of the constitution of the bile acids and related substances. The bile acids are a set of steroid acids whose synthesis begins in the liver with the production of chloric acid, chenodeoxycholic acid, all of which derive from cholesterol. Wieland isolated and determined the structure of a number of these biochemically significant compounds. During his career he also isolated toxins from poisonous frogs and mushrooms.
Who first realized that oxygen gas, O2, was required for fire?
Philo of Byzantium in the 2nd century BCE was the first to observe, or at least the first to record such an observation, that if you placed a jar on top of a candle with water around its base, some water would be drawn up into the jar as the candle burned and eventually went out once all the oxygen was consumed. Although the experiment was well designed, he ended up with an incorrect conclusion about the process. Robert Boyle repeated the experiment but replaced the candle with a mouse. Seriously, and noticed the water also rose up the container. From this experiment he correctly inferred that whatever the component in air was, he called it nitroairus, it was needed for both combustion and respiration. Robert Hooke, and others, likely produced oxygen gas in the 17th century, but didn't realize it was an element as the phlogiston theory, see below, was in vogue at the time. So to really realize that oxygen gas was required for fire, it first had to be, well, discovered.
What is the melting point?
Temperature at which liquid and solid phases coexist in equilibrium.
Do nuclear reactions take place in outer space?
Yes, inside stars. Nuclear reactions occur frequently in stars as hydrogen atoms undergo fusion to produce helium and eventually other heavier elements. Some additional, higher energy nuclear reactions also take place when two neutron stars merge.
Why did Ahmed Swail, Egypt/United States, win the Nobel Prize for Chemistry?
For his studies of the transition states of chemical reactions using femtosecond spectroscopy. Swail was awarded the prize for his work using ultrafast femtosecond spectroscopy to study chemical reactions in real time. That is to say, on the timescale on which they actually take place. Swail's earliest experiments in this area looked at iodocyanide and sodium iodide. He was the first to be able to observe the dissociation and recombination of a chemical species as it actually took place. His great advances in spectroscopic techniques revolutionized the field, and continue to do so today.
Can radio telescopes detect any kind of molecule?
Radio astronomy can only detect molecules with dipole moments. And the stronger the dipole, the easier it is to detect. As a result, carbon monoxide, Ca, is very easy to detect in space because of both its strong dipole moment and its relative abundance.
Why do some prescription pills come in such elaborate colors/capsules?
There's no chemical reason for this. Sometimes pills are colored for branding purposes. Pepto-Bismol, R, is pink. Viagra, R, is blue. Cymbalta, R, is green, and you recognize those colors. It can also help people keep track of which pill is which, and also to remember which ones to take.
Are all polymers linear chains?
No, and this is another way that chemists classify these really big molecules. The major types of polymer shapes, technical term. Topology, are linear, branched, and cross-linked networks. Linear polymers are chains of monomers joined together, like a noodle or a rope. If there is a point along a polymer chain where a second chain starts, like a fork in the road, this arrangement is referred to as branched.
Why would a chemist measure the melting point of a chemical sample?
The melting point of a compound can provide information on whether it is pure and about whether the correct compound has been made. This, of course, assumes that the melting point of the desired compound is already known. If a compound is being made for the first time, knowledge of the melting point can be useful to the next chemist who tries to synthesize it.
What is a diastereomer?
A stereoisomer that is not an enantiomer.
What is a substituent?
A substituent is an atom, or group of atoms, attached to a specific position in a molecule. For example, in the molecule 3-bromopentane, see drawing below. We could refer to the bromine as a substituent on the third carbon atom.
How are isotopes made?
Specific isotopes of an element can be obtained in one of two ways. Either by separation of the desired isotope from a naturally occurring sample or by synthesis of the desired isotope. Since the different isotopes of an element all have the same chemical properties, they can be quite difficult to separate. The separation techniques used to separate different isotopes are thus based on their differences in mass, rather than on differences in chemical properties. Some of the methods used include separation by diffusion in the gas or liquid phases, centrifugation, ionization, and mass spectrometry, or chemical methods based on differences in reaction rates due to different atomic masses. Different isotopes of an element can also be generated synthetically. One way to do this is to fire high-energy particles at the nucleus of an atom. Depending on the situation, this can either cause a particle to be emitted from the parent nucleus, generating a lighter nucleus, or the fired particle can be absorbed, generating a heavier nucleus. It is also possible to synthesize isotopes of some elements by making use of another naturally occurring nuclear reaction, such as when the particles released by one nuclear fission reaction are absorbed by another nucleus.
What is molality?
A measure of concentration defined as moles of solute per kilogram of solvent.
What is an adiabatic?
A process that does not absorb or release energy.
What is Avogadro's constant?
Avogadro's constant is a large number used to discuss large quantities of atoms or molecules. Usually when chemists talk about quantities they can actually see or measure out. The number itself, rounded at 3 decimal places, is 6.022 x 1023. It's just a big number that relates an atomic or molecular mass to the mass of a collection of many atoms or molecules. Avogadro's number of atoms of an element is called a mole of that element, and similarly, Avogadro's number of molecules of a compound is a mole of that compound. For example, the atomic mass of oxygen is about 16 grams per mole, and 6.022 x 1023 atoms, 1 mole of oxygen weigh, about 16 grams. The most recent, and accurate, definition of this constant was 6.0221407.8, 18 x 1023, which was calculated by careful measurements of the mass and volume of 1 kilogram, about 2.2 pounds. Spheres of silicon 28, a particular isotope of silicon, see next chapter concerning isotopes.